Hello, 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 hello. Hey, what is up? Kev, what's up, Darkest Hour? How are you guys doing on this lovely Friday? Should have had that guitar Arduino powered. There's got to be something Arduino related that you can do with guitar. There's got to be. Tuner. Soundboard. Your own little amplifier. The kit comes with some buzzers. You could power those with your guitar. How long have you played guitar? I've played guitar, I think 3 years now. Glue the accelerometer to the string. Ooh, a nice use of emotes, Patrick. Wait, what is the command for that thing? What workshop are we doing? Well, we're going to be doing workshop 4 this coming week. Workshop 3 had a technical issue, but workshop 4, we're set. PWM, pulse width modulation. I'm gonna show you some of the stuff today. RIP Workshop 3, I know. So we will only end up doing 6 workshops. Yeah, because I guess originally we planned for 7. And then workshop 3, rest in peace, with the relay. Servo-powered whammy bar, triggered by accelerometer. You guys have a lot of fantastic ideas for Arduino-related guitar stuff, and I like it. Workshop 3, gone but not forgotten. Hey Richard, happy Friday to you as well. I hope all of you are doing well. I hope you're having a good Friday. At least it wasn't 2020 that took Workshop 3. That's true. It was entirely not 2020 related. It's a beautiful day in Buffalo. If you can see a little bit out the window behind me, it is like bright and sunny and gorgeous. Probably cold, probably a little cold. Hello, Not Prof. Welcome. Welcome. Hope you're doing well. That magnet was the purpose-built failure, so the company gets you to buy more. Man, I spent a lot of time looking into that. Yeah, it's tricky. Yeah, this is as beautiful a day as you can get early March in Buffalo, and I'm happy about it. Let's see. Uh-oh, this title is not right. Okay, we're not looking at relays today. Let's just call it PWM. Pulse width modulation. I need to turn this music down a little bit. So we're getting started here now. Yeah, thank you. So we're going to talk about pulse width modulation and basic DC motor speed control. Okay, so let's do a little bit of recap. We know how to turn off and on devices using Arduino pins. So you can set a pin on an Arduino to high or low, and that's really all that they can do. So they can go high or low. And the Arduino on its own outputs very little power. Little power. I think I put 2 L's in little, but that's okay. So 5 volts at like 20 milliamps. And power is voltage times current. Not professor with a PhD in tying all kinds of knots. Not professor is a PhD candidate at UB who does study knot theory. All of the theory. Okay, so we can interface with external power sources because if we want to do anything more than like turn on or off lights or very low power devices, we need to be able to interface with external power sources. One way to do this is with a relay, which we talked about last time, where a relay is you have an electromagnet which can open and close a switch magnetically. And the Arduino has enough power to turn on an electromagnet and close a switch. And this switch could be the bridge from a high power source to something you're trying to control. Okay, but this is still like on, off control. So this is where PWM is going to come in. Here come the transistors. Yes, our motor controller is going to have transistors. What if we want to produce a signal somewhere between on and off? So what I mean by that is like each pin on the Arduino can be either 0 volts or 5 volts. What if I want to produce like 3 volts, 4 volts, like somewhere in that region? Like DC motors, we're going to look at that today, require a range of voltages to achieve different speeds. All right, this is where PWM, or pulse width modulation, is going to come in. So here's where PWM comes in to save the day. Let me explain pulse width modulation to you. Now, we can't get around the fact that an Arduino pin can only be on or off. Okay, so let's put voltage here. And this dotted line represents 5 volts. And let's make this horizontal axis just time. Okay, pulse width modulation. I'm going to draw a graph here. I'm going to make little equally spaced tick marks on here. And each of these represents a time interval of around 1 millisecond. So actually, I'm just going to kind of change the axis over here. This time is going to be in milliseconds. We're going to start at 0, 1, 2, 3. So this is only 4 milliseconds long. And so the period between each of these is 1 millisecond. Now, what we can do is we can rapidly switch on and off certain pins on the Arduino, specifically the PWM pins. And let's draw an example here. So within each 1 millisecond period, I can turn on a pin for a certain amount of time. So it starts at 0, and then at like the halfway point, so halfway to 1 millisecond, I turn on a pin, and then I turn it off again at 1 millisecond. And let's keep repeating this. So I'm trying to draw each of these pulses like halfway between. Boom. So this is happening very, very, very fast. On, off, on, off, on, off. Each of these we call a pulse. And each of these pulses has a width. So, in this example that I drew, it's half a millisecond. Now, if you send a train of pulses very, very quickly to some device like this, the device is going to experience what we call an effective voltage. And the effective voltage is the average voltage that this pulse train is producing over time. So if you think about this, this is sending a 5-volt pulse, but it's only on for half of the time. So the effective voltage in this case, let's draw it with like a blue line, is going to be halfway. So the effective voltage equals 5 volts divided by 2, so 2.5 volts. So here's the notion. So this is sort of a DC version of how a dimmer switch works. Yes. Actually, we're going to do a dimmer example today. I don't think a dimmer in your house necessarily works the same way, but let's explain this a little bit first. So because we can only turn pins on or off, this is our way of finding an effective voltage somewhere between the on and off, so that what we're providing this signal to, it gets somewhere, a voltage somewhere in between. So this is called, we talked about pulse, we talked about the width of the pulse. So is the thing basically turning on and off constantly? Yes. But think about, I don't want to get sidetracked too much, but think about a first order system if we go back to dynamics. A first order system has a time constant. So it doesn't, like if you provide a step input to a first order system, it'll gradually change state in like an exponential fashion. Now think about this pulse train as like a sequence of steps, kind of intermittently. Because these steps are happening so fast, it's not like the system is going to, respond and then turn off and then respond and then turn off in a first order fashion. The time constant of the systems that we turn on and off is usually much, much slower than the frequency of these pulses. And that's how we can actually, it makes it feel more of like an average to the system that's experiencing these pulses. If you really want to get in deep, you could do, because I know in MAE 340 we simulate systems in MATLAB. You could make a first order system and maybe use LSIM or something like that. I know Mook likes to use LSIM. You could create a pulse train for the input and see what a first order system does in response. Okay. But yes, we're just turning it on and on and on and off. You could also use Simulink. Yes, you could use Simulink. Okay, so how can I change the effective voltage? Well, we modulate the pulse width. So let's do another example. What if I turn on the pulse for 75% of the time? So I know this is a little bit off, but I'm trying to... So I'm just increasing the pulse width. This is going to bump up the effective voltage to 3/4. So if I take 5 volts and then in this case I multiplied it by like 3/4, whatever that is, 15/4. Are there capacitors involved to smooth it out? Well, that's kind of what I'm saying. Like, whatever system you apply this to, it kind of has, like an RC circuit is first order, and it has a smoothing effect. But any system that you apply this kind of abrupt pulse train to, it'll have its own smoothing effect that takes place. Okay, one way that we can define the width of the pulse is using what we call the duty cycle. We define the pulse width in terms of duty cycle. So duty cycle is just, so definition, percentage of time pulse is, let's just say pulse is on during one period. All right, so the first example we did in pink is 50% duty cycle. And then this second one that I did in green, kind of running out of room, but that's 75% duty cycle. And let's write an equation for the effective voltage. Let's just call it V average. Is the duty cycle, and let's say it's in percentage, divided by 100% times the maximum voltage, which for the Arduino pins is just 5 volts. So if you have 50% duty cycle, it'll be 1/2 times 5 volt. The effective voltage is just 1/2. Okay, so that's the idea of pulse width modulation. Let's put it into practice. We're going to do a little example. How to implement this on the Arduino. It's actually really straightforward, fortunately. This is how you do it. You use the analog write command. We've been using digital write a lot, but for PWM you actually use analog write. And you specify the pin number where you want to use it, and it has to be a PWM pin. And I'll show you in a second which ones those are. So you can't do it with every pin. And then you specify the duty cycle you want. Effective voltage, also called RMS. I don't know if that's the same. Root mean square, maybe it is the same. I'll have to check that, T. Jackson. So the duty cycle, though, we have to specify it as a number between 0 and 255. So 0 corresponds to 0% duty cycle. 255 corresponds to 100% duty cycle. And if you want any duty cycle in between, you just have to do it. It's a linear relationship between 0 and 255. So if I want 50% duty cycle, it would be 255 times 0.5. All right, we're going to do a demo to put this to work. We're going to do a demo. And this is one of the things you're going to work with in the next workshop. This is an LED, but it's special. Wait. Don't be blurry. Don't be blurry. I know it's a little blurry, but you can see that there's 4 leads. It's an RGB LED. Okay, so why does it have 4 leads? Well, RGB stands for red, green, and blue. So 3 of the leads correspond to those 3 colors. So there's actually like, can I just type 255 times 0.5 in the code? Yes, you can. So there's miniature LEDs in here. So there's a red one, there's a green, and then yes, the 4th one is ground. So you see here, I have a red wire for the red LED, and it's going through a resistor to the red lead itself. Green is for the green LED, blue is for the blue LED, and then black is for ground. And so the resistor is just to limit the amount of current that's going in here. So if you look on here, PWM pins, focus, are going to have a squiggly next to them. Please. Please. Oh, there we go. Okay, you can kind of see it. Maybe it's too bright. Yeah, it's got like a tilde. And so all these pins that have a tilde next to them are PWM pins. So 11, 10, 9, 6, 5, and 3. So I'm going to connect... I'm going to connect the black to ground. And I'm going to pick pins 11, 10, and 9 for RGB. So 11 for red, 10 for green, and 9 for blue. All right, so we just plug that in, and then we're going to make a simple code to work with this. This is going to be really basic. Let's move this. Let's move this down. Okay, so I'm going to define my red LED pin. I think I plugged that into 11. And I have to specify this as an integer. And then we're going to copy these. Red, blue, green, and I think this one was 10, and this one was 9. So we're just defining the pins, and then we're going to define each of these pin modes as outputs. So this is just the same kind of code that we do for turning on LEDs. Makes sense. Blue. Can you pulse modulate with all the colors? Can you pulse modulate with all the colors of the wind? Yes. Green was, oh, thank you. Green was 10. RBG or RGB, I don't even know. Okay, so what we're going to do in the loop, first we're just going to, what did I want to do? Let's just turn on the red one. Analog right. So we're going to use the red LED pin, and we have to now put the PWM value. So what I like to do when I make PWM codes is I like to make a variable for the duty cycle, and I make it a double. And so this 0.1 represents like 10% duty cycle. So what I like to do is for the PWM, I take the duty cycle and then I multiply it by 255. So this is going to take 10% of the time the pulse is going to be on for the red. And how about we just upload this code and run it. And hopefully this LED turns red. Tools, port, okay, go to the right one. What does the double mean? It allows you to define decimals. Oh, buddy. I know the color, it doesn't look as true, but it's red. You got to believe me. It's a faint red. Let's increase the duty cycle to 0.8. And you see it's brighter. And then we can go all the way up to 100% duty cycle. And hopefully it doesn't explode. Beautiful. Now, you can, let's see. So we can dim, we can make a little dimmer. Let's do this. We're just going to make like a little delay in the code of like 100 milliseconds. And then we're going to say duty cycle equals duty cycle plus 0.0. So we'll boost it up by 1% every time. And then we'll rewrite it. And then I'm going to do something here to just be careful. Because the duty cycle is going to be increasing every time we go through here. But if duty cycle is greater than, if I put if I put a paper next to it. Kind of. Okay, but if duty cycle becomes greater than 1.0, then let's just start the duty cycle over again. So this is going to hopefully make it like grow in intensity over time. Oh, you can see it. And then it's going to start over. I think. Oh, yeah. Then it goes back to the beginning. So I just wanted to show you that the voltage keeps increasing. How can I make... If I could reflect it off of paper. Oh, and then it's breathing. It has become sentient. All right, we got to move on. So, but I'm going to... There's so many things you could do this, because we didn't even play with the others, right? Green, blue, I mean, there's so many. Let's just, I don't even know what this is going to, wait, this will make them all even. And I'm just going to do this. This will just change, this will make it a different color. Skynet! I know. Oh, whoa. That's pretty cool. So it's becoming proportionally more red because the other ones stay the same. But there's a lot you can do with this one. This is fun because you can make like any color of the rainbow. Okay. Something that I thought would be fun to do is this kit comes with a joystick, and you could change the percentage of like red, green, blue by moving around the joystick, and you could do it in real time. Make the green LED duty cycle 255 times 0.25. Times 0.25. Your wish is my command. Red plus blue plus green equals black. Wait, let's boost up how quickly it goes. Wait, we'll do this. Zoo, zoo. Oh, it's breathing! It has a heartbeat! More boost. Okay. So, okay, we gotta stop. We gotta move on. But you're gonna do something like this with your workshop. Playing with PWM. Let's go back here really quick. Okay. So let's talk about. Oh, come on. Let's talk about DC motors, then we'll do another quick demo. So I won't talk about the mechanism, the physics of a DC motor, but I'm going to post an awesome YouTube link to explain how it works. It's like maybe a 3 or 4 minute video, but it has great animations. It does a better job than I can do. But the way that you can think of a DC motor in terms of its functionality is we provide voltage and current, and it provides some kind of rotational kinematics. So you can use this for precise, like, rotational control of something. I think I might have showed you a little balancing robot, and it balances using 2 DC motors connected to tires. Those are its little wheels, its little legs. And you could also think of it as a production of torque. So this is functionally what its place is. So if you increase the voltage, also check out some of AVE's videos where he tears brushless DC tools. Nice. This produces increased torque on the shaft of the motor. And as you can imagine, that increases the speed. Oh, tears down. That sounds like a really great video to watch. Because I think the way to understand a DC motor is to look inside and start simple. If you just break one open, it can look complicated inside. But the video, I'll post a link for it. It starts at very basic. Now, if you provide a voltage, it doesn't just keep increasing in speed infinitely. The motor, for a given voltage, reaches a steady state speed. The reason it doesn't keep increasing in speed is because of what we call back EMF. And this video can talk about that a little bit too. But you could make a graph like this. And this is going to be related to our first assignment. Because after this workshop with a DC motor, we're going to have an assignment related to the DC motor. And it's going to be a calibration assignment. Because there's a calibration relationship between the voltage that you give a DC motor and its steady state angular velocity. And the relationship, like if you took some sample points, it's pretty linear. So, as you can see here, if I want to achieve a different angular speed, I have to provide a range of voltages. And so this is where PWM comes in. I don't want the motor just full speed or no speed. If I want to be able to achieve intermediate speeds, we use PWM. All right, let me show you this. I'm going to show you what we call a motor driver, because there's an intermediate piece here that we need. So in your kit, you have a chip. Let's see if it'll unblur. Maybe. Well, okay, you get the idea. But if it focuses, you can see the name on the chip, and it's called an L293D, I believe. So you'll have to be careful because there's two components in your kit that are shaped like this. I wouldn't call it a microcontroller. I would call it an integrated circuit. Wait, can I get it bright enough to really, no, other way. But you can kind of see there's some text on here. But one of these, oh, actually the way you can tell these apart is there's like a little circle on here too. But this is called a motor driver. And this, you can think of it as a relay, but it's more sophisticated than a relay because it uses transistors instead of mechanical action to open and close switches. Try putting your hand behind the board. Well, I think it's in decent focus now. So what we're going to do, I know there's a bunch of wires here, but essentially we're going to send a PWM signal from the Arduino to here, the motor driver. And then this motor driver is going to open and close switches, but they're going to be transistors, very quickly. And it's going to divert power from this guy, this little power board. Well, we have like a 9-volt battery that we plug into this. And what that does is it energizes this rail over here on the red side with 5 volts of power. So this is an external power source. And this motor driver is going to be taking the power from that external power source, and it's going to divert it to the motor. And as you can see, when the motor came in the kit originally, it had some beautiful, beautiful wires that came off these leads, and mine broke. And I wasn't like rough with this thing, so I'm expecting probably a lot of you are going to break off these leads. So don't worry too much, because I think I have a way of attaching this. But anyways, let's plug this. Let's plug this in. Let's plug this in. So I'm going to take our old circuit. I'm going to dismantle it. I kind of have this ready in advance. Why can't you drive the motor directly from the board? Well, number one, because the Arduino board cannot produce enough power to effectively rotate this thing. It takes a certain amount of voltage and current that this Arduino board just simply can't provide. So that's the main reason. The other reason is motors have inductors inside. Anytime you have a coil of wire, that's an inductor. And when you energize quickly and de-energize an inductor, you get the issue of back EMF. You can have inductor kickback, and that can fry your poor Arduino board, or damage the pins at least. So only this guy, I know, Workshop 3, that's why, anyways, this guy has all the protections in place, the diode, whatever, and only this guy is going to be connected to the motor, actually. So this is the little shield between you and your board, your protective friend. Okay, so this pin is going to go to ground. So you're going to be doing this in your next workshop. You're going to be connecting this guy. I think the green, I don't even remember which pins. I got to rip shop 3. Wait, this one won't fail. Guys, this one won't fail. Pwm 5 and something like this. I heard a while ago electric motors like to spin as fast as they can. I mean, they probably enjoy it, just cutting loose. Now, oh shoot, you can't post hyperlinks in the Twitch chat. You can post it on our Discord. Okay, so I won't get too much into it here, but the gist is we have these 3 pins from the Arduino connecting over here. 2 of these pins, so the orange and the yellow, these are going to help us change the direction of rotation of the motor. Okay, so that's the responsibility of those. This green one is going to send a PWM signal over here. So this is basically allowing us to change the amount, or this allows us to change the percentage of power that we're going to grab from the external power source, which is going to be this 9-volt battery plugged into here, which regulates it down to 5 volts. So the PWM is responsible for that. Then I have these red and black wires that are only connected to this chip, this motor driver, and I have them plugged in over here, and you'll see some resistors in here, and you'll be like, what the heck are those doing there? Okay, the reason I have that is because I broke the little leads off of this dude. So my way of working around it is basically I just need these leads to touch some metal. So I'm having them connect to the metal of these resistors. Maybe you can see, maybe if I tilt this, you can kind of like see. Yeah, you can kind of see. I have this metal from the motor that's just touching the metal from the resistors. And it's just the sorry state that I'm now in because I broke this, and it's their fault that they soldered this so poorly. But anyways, the power going to the motor is going into this row of the breadboard, and then the resistor is in that same row. So that wire is going to be carrying the power, and it's going to touch this lead over here. And then same with the other side. It's just, so that's, oh no, it fell. Okay. So if you break your motor, you're going to have to do something like this. You're going to have to do the walk of shame. +5 to people who keep the wires. Dude, if you can keep it connected, I'm going to be really impressed. Because I tried to treat this thing delicately. Okay. All right, because we're running out of time, I wanted to build this code from scratch, but we're just going to have to jump ahead. Let's go over here. Let's go here. Okay, so this code actually looks pretty similar to the last one. Is this for a class? Yes, it is. At the University at Buffalo. We have a PWM pin. That's the green wire plugged into pin 5. And then 2 of the pins were for changing the direction, remember? And then I'm also playing with the duty cycle. I set all of those pin modes to output. So to specify the direction that you want to spin the motor, you set one direction pin to high, the other one to low. And if you want to go the other way, you switch it. So you make that one low, then this one high. And that's what I'm going to do below. And then to send the PWM, you do it just like we did for that LED. So this code is going to spin the motor in one direction with some duty cycle. It's going to wait a second and then spin the other way. All right, let's try it out. We got to connect the USB. We got to upload this code. And this motor, I'm going to have to like hang it off the edge of the desk. Oh no. Oh no, I dropped it. Oh no. That's... Ugh. The lesson you learn from this is don't break those wires, okay? All right, so I need to plug in the RIP workshop. No, don't say that, Calvin. We're gonna plug this in. 5 ground. Wait, let's make sure this is plugged in right. That's plugged in. This is plugged in. That's plugged in. 543. The wires may not be the issue anymore. I just dropped it again. Okay, all right, what I'm going to do, I'm going to disconnect this fan for a second. Let's go back to this. You can see this a little better. F, yeah, I know, right? Wait. Set 1 of workshop 4. Throw the motor across. No, that's not the first step. Wait, I'm actually confused. This was working. Okay, I have the power source plugged in. Yeah, that was the second step. Might be better if the motor isn't right next to the edge of the table. Okay, that was because I had the fan and I needed it not to like hit the... I needed it not to hit the thing. Okay, let's make sure. Your resistors don't look connected. Wait, come on. I mean, like you can see what's going on here. Like I have the power coming in to this row, and I'm just trying to connect the leads. I'm just trying to connect to the... I just need some metal to connect to. I wonder if the... Wait, duty cycle 0.7 times 255... Wait. When I did this before, it wouldn't work because the chip wasn't fully in the board. My chip, okay, it's in there good. Let's change the duty cycle real quick. I wonder if I broke... Oh wait, I wonder if this pin isn't all the way in. 5, 4, 3... Ground, power. Oh! Okay. Okay. You hear it now. You hear it. It's a little tricky to just get the connect dubstep. Yeah, I know it's. Yeah, the joy of making. I know, guys. This is just what we have to deal with. We have to use the stuff in the kit, okay? Okay, so I know it's hard to see because I took the fan off. Maybe, but now the fan could hit the wires. This is the trouble that I have. Let's make some dubstep. Oh my gosh. This is tough. I just need those leads coming up, and then I need space. Give me some space. It wants to work really bad, but my finger's in the way of the... Oh my goodness. Okay, so it's kind of a it's tricky to keep the fan on. Okay, if you want to change the speed, you change the duty cycle, right? Did you take a clip? Use the leads instead of the resistors? You mean like this? I mean, I guess... Oh, actually, this is promising. Okay, it's spinning, but... Wait, no, grab 2 more leads? But what would grabbing 2 more do? Because what would I do with the other 2 leads? I mean, I guess this is... I really want to get the fan on. Just solder 2 wire. I know, like, but most people in this class won't have any soldering equipment, so I want to use solutions that are only in the kit. Okay, so this works pretty well, but you have to hold it yourself. I was trying to come up with a solution where you could just like leave it. So like stuff that you're going to do in the workshop is you're going to do some basic tasks like this. Is there current running through your hand? No. Twist them around the terminals? Oh, that's not a bad idea. Because the current is going to take the path of least resistance. Or, I mean, it'll still travel a little. We twist them around. Electrical tape. Oh, yeah. Easy mode, a 12-pack of hobby motors is $11 on Amazon. Yeah, I wouldn't mind if you wanted to shill out for like a non-broken motor. Wait, but I don't want to twist these because I might want to use these jumpers for something else. Well, I mean, there's a bunch of jumpers in the kit, so let's. What if I bend this guy? Is this what you meant? Seems like including even one alligator clip would be... I agree. Could I use Scotch tape? Actually, probably that's not a bad idea. That's probably not a bad idea. I don't think I have enough length here to really... For $45, you'd think everything would work properly. Well, I don't... Well, okay, because $45 got 3 different motors. Use a glue gun. Ooh, that's a good one. Don't use the terminals to pin the line. You think you're so clever, don't you? Oh man, it probably shouldn't use your finger either. Okay, let's see this. Let's see this. Rate the product. No, I'm actually, like, overall, I'm very happy. Oh, good grief. Yeah, I mean, like, usually an Arduino Mega itself... Oh, dude. Wait, we need to disconnect the power. GG. Oh, here comes the brake from bending it back and forth. I mean, I guess that's the other risk you run. That's not too hard to do. Okay, so I have the power disconnected right now because otherwise this would just... I mean, it wouldn't hurt me. It would just spin that fan around. Wait, I need a little less space. Rip to these jump... I know. But this is a good solution. What if I break off the leads on the motor? Then that would be the end of everything. Guys, look at that. Oh wait, that's not super secure. This is challenging. Look at that. All right, let's plug in the power again. Oh, this is a perfect example why you need external power. Because if you look right now, the 9-volt battery is not connected here. Now, the only power coming in is well, it's from the PWM pin itself. But now the external power source, ooh, this is nice. Well, the trick this semester was that, like, I can't really provide you with anything because everybody's remote. And so it needs to be something you can do yourself. Calvin says we're going to have a hell of a time doing it. Well, this is just if you broke the leads, by the way. I think most of you won't have this problem. But because I was pretty gentle with this thing and I still broke it, I think there's a chance. Oh, no. Oh, no. Okay. It's doable. It's doable, guys. Again, is this for a school? Yes. This is for school. This is called MAE, Lab 1, Mechanical and Aerospace Engineering Lab 1 at the University of Buffalo. Guys, thank you for hanging out today. Learning a little bit about PWM, pulse width modulation. This is going to be our workshop next week. That'll be up this weekend, all the details of that. Homie getting some free knowledge, that's right. That's absolutely right. Hey guys, I know this is the part of the semester where things start piling up, it starts getting tough. So I encourage you, stay in there. Stay in there. You're going to make it. I know junior year especially is heavy. So I applaud you guys for just keeping your head in the game. Yes. As Bob Ross would say, you can do anything. You can do anything in your world. In your world, you can do anything. Oh, I love Bobby Ross. He's a good guy. How's senior year compared to junior year in your opinion? Well, I think some people in this class are seniors. They can probably directly comment on that. But I would say, in terms of course load, I think it's a little lighter. Because you have something like, you have your design course, which isn't like light, but it's like a long-term project that you work on. Whereas the classes you take junior year, it's kind of like you're in the grind always. It's like an assignment is due this week, another assignment. And so I think senior year, it can be a little more spread out. And I think that makes it, I mean, there's going to be times senior year where it really piles up, but I think it's less consistently heavy. I don't know if seniors here can comment on that. Did you drink mate? I love mate, but I haven't had it in a little while. I enjoy mate. Yerba mate. I had a lab mate from Argentina, and he introduced me to mate, and he got me my first mate gourd. You're from Uruguay. Okay. Yeah. Oh, man. I enjoy it. Mate is a tea, if you're not familiar. Are you able to apply for Twitch affiliate status yet? I think so, but I'm not going there because I don't want commercials on here. Wait. What do you need to be affiliate? Is that the... Because I hit the first level, like whatever that is. Because there's like affiliate, then there's partner maybe or something like that. You were able to apply for affiliate but almost hit partner. I think I'm able to apply for affiliate. Wait, what's the difference? What is it? Actually, I don't even like know exactly what both of those mean. I think affiliate lets you have subs, but I don't want people to pay. 10 viewers average, 20 hours. Okay. Yeah, I meet the affiliate thing. Huh. Partner gives you that purple check mark next to your name. Does it come with anything in addition to a check mark? No, I don't want commercials or anything. This is supposed to just be, you log in, straightforward. You have direct access to the content. You don't have to watch a Burger King commercial to enjoy a lecture. When I jump into a channel on Twitch and a commercial comes up, I just go to a different channel. Unless I like really want to watch. Like if it's chess or something, I'll stay. Affiliate and partners also have emotes and bit donations. Okay, gotcha. Well, wait, we already have emotes. I already have all the emotes. Wait, how do I, what's my pog? See, I already have emotes. Okay, in case you're curious, lecture has been over. We're done with the content. I'm just kind of just enjoying hanging out with you at this point. But we won't be covering any more technical. Oh, emotes that can be used on other channels. You said in an email that the lab is due on Tuesday for online students, but the deadline on UB Learn says Friday. It says Ranger. Okay, the reason for that is everybody has like different deadlines depending if you're online or if you're an in-person student. And when I make the assignment on UB Learns, it only allowed me to specify one deadline. So I just put the last day. But if you're an online student, it's still Tuesday for you. I mean, the other workaround is that I could make an individual assignment for every section, but then I'd have to make like 8 or 9 different assignments, and I was just like, no. I want it all in the same place. So it's just UB Learns. It's an issue with the platform. Hey, you're welcome, Ranger. Guys, it's a beautiful, sunny Friday. I hope you've had a great week. I really do, I mean that. You had a test today? How was it? It was easy though. Good news. An easy test on a Friday. Alright everybody, I think I'm going to log out. I'm going to eat some food. That's my first order of business. Are you going to be later on Discord? I might check in. Just see how people are doing. Hey, thank you, Not Prof, for dropping by. It's a pleasure as always. All right, everybody. Adios.